Welcome to qnawire.
We have here a free body diagram of a disk attached to an arm with the point O. And what we're asked to do is we're asked to find the angular momentum about that point O using this equation and to compare our answer to this answer in red, which was calculated in the sample problem. So to first start solving this problem, we're going to find what the total angular velocity is in this system. So the total angular velocity, which I'll label as omega t, that's going to be equal to the angular velocities in the counterclockwise direction. So omega 1I minus the angular velocity in the clockwise direction. So omega 2j. And I'm also going to write the equation for the angular velocity at the point C, which we can write as the total angular velocity cross the RC position vector. So what we can do is we can take this term here and plug it into omega t here. And we'll get a new equation for omega c. So we'll get a new equation for omega c, which is going to be equal to omega 1i minus omega 2j cross, and for this RC vector, we can plug in the length Li, this length Li, minus this radius j. And that will give us the position vector for RC. So it's going to be Li minus Rj. So we can now compute this cross product here. And after computing the cross product, we'll get a value of omega c that's equal to L omega 2 minus omega 1 R K. And we know that the angular velocity at this point C is 0. So what we can do is we can set this equal to 0, and we can solve this equation now for omega 2. So we solve for omega 2, and that's going to give us omega 1 times R divided by L. So what we can do now is we can take this expression here and we go back to our equation for the total angular velocity, and we can plug it in for omega 2. So we can now write that the total angular velocity is equal to omega 1i minus omega 1 times R divided by L J. So next what we're going to do is we're going to look at our free body diagram, and we're going to take moments of inertia about the point G on the disk. So for the x component of that moment of inertia, we know we can write that as 1 over 2 times mr squared. For the y component, we can write that as 1 over 4 mr squared. And for the z component, we can write that as 1 over 2, 1 over 4 mr squared. So now the equation for the angular momentum about the point G. So we're going to solve for this part of the equation, h of g. H of g, that's going to be equal to I of x times omega xi plus I of y times omega yj plus I of z times omega z k. So what we can do now is we can plug in values. So plugging in values for I of x, then omega x, and then I of y, and then omega y. And then for the z component, we know that the angular velocity in the z direction is going to be 0. So we can just write this as 0k. And then simplifying this equation, we write it as 1/2 times mr squared times omega 1i minus 1 over 4 times m omega 1 times r cubed divided by lj. So we're now going to use this equation here. And I'll write it again down here. So writing again that equation, h of O is equal to the r position vector cross the mass m times the velocity vector plus h of g. So using what we have, we can now write h of O as li cross m times omega 1 rk and then plus h of g. And then we can compute this cross product here. This cross product here. And then we can rewrite this as negative m rl omega 1 j and then plus h of g. And we can again simplify this as 1 over 2 times mr squared omega 1i minus m times L squared plus 1 over 4 R squared times R omega 1 divided by Lj. And this is the same answer as given by the problem, which I wrote in red here. So what we calculated is also the same as given by the problem.